We have been talking about taking derivatives. Today we're going to cover our last big topic that allows us to basically finish off taking derivatives of just about any type of elementary function that we come across. Now we already know how to do things like polynomials in general. We can do any polynomial we want. Now we can do rational functions because we have the quotient rule. You remember what the quotient rule is, right? Say it with me. Low d high minus high d low over low low. Exactly. You can also do the product rule, which is the first times the derivative of the second plus the second times the derivative of the first. Okay. And the nice thing about the sums and differences, the derivative of the sum is the sum of the the derivative of the derivative of sum is the sum of the derivatives, and derivative of difference is the difference of a derivative. I don't think I went through that in class, but that's the way that I remember that as well. The last tool is the chain rule. Now, when or why do we need a chain rule? Can y'all read that all right? Minus the fact that it's bad handwriting. Can you see it, I guess?
Oh.
Yes. Okay. So why do we need a chain rule? Well, think about functions like this. What about y is equal to the square root of x squared plus 1? Now the problem with this function is that we have, yes, a tool to take the derivative of a square root. We have, if we didn't have the square root on there and just had x squared plus 1, we could take the derivative of what's inside. But the problem now is the square root is around or surrounding the x squared plus 1. It's not a product, it's not a quotient, it's not a difference, and it's not a sum. What if you had something like y is equal to the sine of 6x? Also, we got a function that we can take the derivative of inside another function that we can take the derivative of. Y is equal to 3x plus, say, 5 all squared. This one we could probably multiply out and get the derivative after we've FOILed by doing the square, but what if it was as bad as something like 3x plus 5 to the 50th? Right? You wouldn't want to multiply that out, right? If all I had done was something to the 50th, like say I just had x to the 50th, you can actually use the power rule to get that one pretty quickly, okay? Or maybe even some of our other functions, like our transcendental functions, like the exponential or the tangent of x squared, okay? All of these are not products, quotients, differences, or sums. In fact, what I would call these, a better description is they are functions inside of functions. Right? Or the more mathematical terminology for that is what we call composition of functions. Right? Remember talking about composition of functions, I hope you do, back in chapter 1. All right, so let's introduce what I'm going to call the chain rule. Okay? And here it is simply stated. If, say you have y is equal to some function, and I'm going to call it a function f of u, and then u is some function of another variable of x, okay? Or another way of thinking of this is y is equal to some function of another function of x, f of g of x. Okay? Then, the way you find the derivative, dy dx, will be you take the derivative of y, which is this function right here, with respect to its variable u, and multiply it times du dx. Well, what is u? U is that inside function. Okay? Or, thinking of it like this guy over here on the right, if I wanted to take the derivative of f of g of x, Okay? In essence, what you do is you take f prime, leave g of x inside of it, and then multiply this by the derivative of g. Right? That is, in effect, what I have written here on the left. That's a y right there, in case you can't tell. And this over here, this is y with respect to u, leaving u inside of it. Now, here's the way that I think of this. This right here is like the derivative of what I call the outside. You have a hard time seeing the bottom. Let me scoot that up a little bit. Okay. And this is like the derivative of the inside. Okay? So the chain rule is basically like this chain that links together. You take the derivative of what's outside and then multiply by what I'll call the chain. Multiply by the chain is to multiply by the derivative of what's inside. Okay? The reason it's called the chain rule is that you can actually have not just one function inside of another, and we'll see this with an example later on, but a function inside a function inside a function, and so on. Right? You can actually have these things nested so that you don't just have one function inside of another, but maybe a function inside of a function inside of a function. So when you take the chain rule and apply the derivative, you take the derivative of the outside times the derivative of what's inside. But then that may have another thing inside, so when you take the derivative of that, you have to take the derivative of that times the derivative of what's inside that. And so you have this chain linking together. Okay? So think of this in terms of a few example functions. If I wrote down a function like 1 over x plus 1. Let's think about what the outside is and what the inside is. Okay? In terms of, let's say, using u as the variable for the inside. The outside function, to me, this I see is something that looks like 1 over u, where u is x plus 1. Do you see how if I were to have plugged in now u into the outside function, I actually have the original function. So the outside function is like 1 over u, the inside is like u equals x plus 1. The beauty of that is that I can take the derivative of this, right? Just think of it as u to the minus 1 and use the power rule, or I can take the derivative of this, right? What about y is equal to sine 2x? What would you say is the outside function? So y is like sine of u, and u is like 2x. Right? So the outside function, the container function, is the sine of something, and the thing that goes inside that container is 2x. What about y is equal to the square root of 3x squared minus x plus 1? What would be the outside function? Exactly. It's the thing on the outside. It's the container. Does everybody see that? And then what is u then? It's the guy inside. 3x squared minus x plus 1. Exactly. So we need to begin to thinking like outsides and insides. Once you can think that way, the chain rule becomes pretty easy. Tangent squared of x. Now this one's a little tricky. What's the outside function? U squared. Now if you thought tangent of x, think through, don't write this down yet. In fact, I'll write this in red. If I wrote down tangent of u here, and then I put u is equal to, say, x squared, the problem is that's tangent of x squared, right? When I plug this into there, which is not what my original function was. So what I really want to do is I want to think of this guy. Anytime you see a square like that, that's like tangent of x quantity squared. See how now the container function is the u squared. Oop, go back. And then u is tangent of x. Hey, that darker is easier to see. I'm going to keep using that. Okay? All right. So applying this chain rule that's up here, which means, again, when you take the derivative of a function inside of a function, you take the derivative of the outside function and leave this inside right there, right? Just like it's inside up here, you take the derivative of these outside functions, but leaving the inside function in there. And let me show you what that means for a few examples here. So let's jump down and let's do an example. Let's find dy dx for y is equal to x squared plus 1 quantity cubed. So dy dx is, now if you need to write it down off to the side, feel free to do this. You're going to see that the outside is u cubed and the inside is x squared plus 1. But I do this all in one step in my head, right? I treat this guy inside here, I just leave him alone, and I think of how do I take the derivative of the outside function. If that was just u cubed, I would take the 3, move it out front, right, and drop this up here by 1. Right? If that was a 3u squared, it would be, sorry, if that was a u cubed, the derivative would be 3u squared. But you leave the u in there, so you leave the x squared plus 1 right there. But don't forget to multiply by the chain. So what's the derivative of what's inside? 2x. And you always got to simplify after you apply the chain rule, so let's put the coefficient part together. So 3 times 2x is 6x times x squared plus 1 quantity squared. That is your derivative. Questions? Does that make sense? Yes? No? Couple of nods? Question?
Okay, the 2x came from
The 2x right here is the derivative of that u, right? Okay, let's do another one.
All right.
Thanks for being excited about that, by the way. F prime of x for f of x is equal to 3x minus 2x squared cubed. All right, try that one on your own. Should be fairly similar. I'll give you just a second. What'd you get? What is f prime of x after you simplify it? Anyone? Anyone? What'd you get?
I got 9 minus 12x times 3x minus 2x squared.
Wait. Slower. 9 minus 12x times
3x minus 2x squared quantity squared.
Okay, so you went ahead and multiplied in that 3, right? Which is fine. I mean, there's going to be some subjectivity to what we considered as finely simplified. I could obviously multiply that out further. I would actually accept this as well. At this point in the lecture during class, unfortunately, we lost audio, so I'm going to have to kind of continue and narrate by putting over sound over what we did. Now, anyways, as I was discussing, what we actually will accept here is 3 times 3 minus 4x times 3x minus 2x squared, quantity squared. The reason being that you can multiply into 3 or not, okay, either way. Again, because the audio messed up during class, what I have to do here is basically doing a voiceover on the existing footage that we filmed during class, so that we can now talk about some additional examples. I'll go ahead and put the voiceover on this section and see what we got. So the next question is, we got g of t, which is equal to negative 7 over 2t minus 3 quantity squared. Of course, we want to try to find the derivative to this. Now, we got a couple of choices on this. You can try to use the quotient rule in order to find the derivative here. The quotient rule would be, of course, low d high minus high d low over low low. Or if you rewrite it as negative 7 to the times 2t minus 3 all raised to the negative 2. In fact, you can use the power rule as a technique for doing that. Okay, so power rule and then the chain rule, because you've got that function 2t minus 3 inside. Alternatively, again, what I suggested before is you could use the quotient rule. The quotient rule would give us the same answer. However, it's going to be messier in general. So anytime that I can rewrite this thing as just a coefficient times a quantity, like 2t minus 3 all raised to the negative 2, that's going to be my better option. So let's do that. Let's use the chain rule to calculate or evaluate the derivative for this function g of t. Okay? So let me grab my green. I'm going to take the negative 2. I'm going to bring it out front and multiply it times that negative 7 and then times the derivative of what's inside. So negative 2 times negative 7 gives me a 14. And then leave the inside alone, 2t minus 3. Then you drop that exponent by 1, so that's a negative 3, times the derivative of what's inside. Now what's inside? 2t minus 3. So what is the derivative of that? It's 2. Again, just always remember to multiply by the chain. Whatever's inside, multiplied by the derivative of what's inside. So that gives me, if I multiply the 2 times the 14 is 28, times 2t minus 3 raised to the negative 3. Generally, we don't leave it simplified with negative exponents, so let's rewrite that as 28 over the quantity 2t minus 3 raised to the positive third power. There's your final, there's your final answer. Now, where we can get into the most trouble in this section is that using the chain rule, we often get some complicated looking expressions, and so I wanted to put forth a few examples here where we have to do some simplifying, so you can see some strategies that we can use to simplify our derivatives once we have found them. Okay? So, for example, let's think about this function. F of x is equal to x squared times the square root of 1 minus x squared. Now this one's going to require a combination of rules to answer it. In fact, what's the first rule we're going to have to apply to find the derivative? You see that we've got a function here times another function here, right? There's not like a container function that's just outside of everything, right? We actually have to split this thing into two things and multiply it together. So we're going to use the product rule, PR for product rule, which means first times the derivative of second plus the second times derivative of the first, just reminding ourselves. All right, so let's do the first times the derivative of the second. So the first is x squared times now the derivative of the second. So I'm going to put this in a bracket here. So notice this guy right here, this second one, is actually 1 minus x squared to what power? Square root is the same thing as 1/2. All right. Anytime we take derivatives of square roots, we have to remember that square roots are 1/2 powers. So we'll take the 1/2 Bring it out front. 1/2 times 1 minus x squared. Leave the inside alone. And then 1/2 minus 1/2. Negative 1/2. Then times the derivative of what's inside, which is negative 2x. Because derivative of 1 is 0. Derivative of minus x squared is minus 2x. So keep straight what you're doing. We're doing first times the derivative of the second. Derivative of the second was, using the chain rule, 1/2, 1 minus x squared to the negative 1/2 times the derivative of what's inside, or negative 2x. Okay? Plus the second, which is the square root of 1 minus x squared. Actually, I tell you what I'm going to do. I'm going to go ahead and leave everything either in exponent form or radical form. Let's not mix the two. So let's put that as 1 minus x squared to the 1/2 power times the derivative of the first. Derivative of x squared is 2x to the first, or 2x. Okay, so now we need to simplify a little bit. First thing I'm going to do is just combine some of these things together, like these monomial terms right here. Just go ahead and multiply those all together. I end up with a minus x cubed times 1 minus x squared to the negative 1/2. Right? If you take x squared times x, you get x cubed. 1/2 times minus 2 is a minus 1/2. So I multiplied all those monomials together. Over here, I'm just going to move that monomial term up to the front. 1 minus x squared to the 1/2. Okay, and now here's my suggestion. And this is a pretty good general rule to help make these things look as simple as possible. Whenever you got an expression like this, factor out the least powers of each term. Now what I mean by that is, for example, the x right here. This one's raised to the third power, this one's raised to the first power, so factor out one of them, x to the first. So x to the first I'm going to pull out. Now look at this second term right here, this guy right here, and this guy right here. Which one of those has the least power, the lowest power? It's the negative 1/2. So what I suggest we do is we pull that out. So pull out 1 minus x squared to the negative 1/2. And see what's left behind when you factor those out. So if we factored out an x out of this first whole term, you have 2 of them left, right? So minus x squared left. You also factored out a 1 minus x squared to the negative 1/2, so that's completely pulled out. So all you got left in your first term is negative x squared. Make sense? So far? Okay, what about the second one? Well, you pulled out the x, you still got the 2 left behind. Now the question is, what's left behind when you pull out an x to the minus 1/2 from x to the 1/2? A 1. You're subtracting the exponent. So you're taking the 1/2 that's here minus the minus 1/2 that's here. Then what's left here is a 1 minus x squared to the first. You can either write it down or leave it assumed. Okay? And so just as a side note, I'll put this here in red for me at least so you can see it on the screen. That 1 right there is the 1/2 minus a minus 1/2. You factored out that one, then that's what you're left with. Now this will be a little bit simpler once we write this out. Let's simplify inside the parentheses here. So if you distribute this here, you end up with a minus x squared plus 2 minus 2x squared. Agreed? And this first term over here, rewriting this with the negative means move it to the bottom. I can rewrite this as x over the square root of 1 minus x squared. So what this now looks like is x times 2 minus 3x squared, all divided by the square root of 1 minus x squared, which is a much cleaner form than we had, say, right here. Okay? I mean, this is correct, but this is simplified. And you're going to learn, the more and more we work with these functions, especially when you have to start doing things like second derivatives and third derivatives, you want that first derivative in the neatest possible form that you can get it. So using this trick right here of factoring out the least powers is something you're going to want to get the hang of. All right? Let's try another one. I'll leave a little bit of space up there so you can see what we got. All right, example. Were there any questions, or did I make any jumps on the previous one that I need to go back to, or are you okay? We're okay? All right. And again, you can go back and take a second look now that I've got this hopefully on film. You can, not literally film, but digital ones and zeros that can be played again and again and again, if you desire. F of x is equal to x over the cube root of x squared plus 4. Now, of course, again, I'm asking you to find the derivative. What's the first thing you want to do before you ever find the derivative? Anytime you see a radical, change it to a fractional exponent. So how do we rewrite cube root? 1/3. So x squared plus 4 to the 1/3. And of course, we have a choice. We can use moving that up to the top and use the product rule, or we can leave it on bottom and use the quotient rule. Now, generally, if it's a choice like that between converting and using the product rule or just doing the fraction, it's going to be just as messy with the product rule as it is with the quotient rule. Here is a second point in the lecture, again, where we lost audio in class. I don't know what the bug was, but I'm going to record now after the fact, doing the best I can to remember what was said during class as we took these notes. If there are pauses here, I apologize. The whole point of this is, again, so that you can have access to these lectures outside of class, and especially those of you that were unable to attend class today. All right, so again, we're looking at this function. We're going to try to find the derivative. As I was saying before, you can do this with the quotient rule or with the product rule. We're going to go ahead and use the quotient rule because, generally speaking, with the product rule, you don't gain anything. I mean, it's not any simpler in the end than using the quotient rule. So remember that the quotient rule is low d high minus high d low over low low. So I'm going to take the to get the derivative, I'm going to take the denominator times the derivative of the top minus the numerator times the derivative of the bottom, all over the denominator squared. That's our quotient rule hoedown. So the denominator, low, is x squared plus 4 to the 1/3 power times the derivative of the numerator, which in this case is 1. Derivative of x is 1. Times high, d low. So now we're going to take the derivative of the denominator, which is now a composition of functions. We have x squared plus 4 raised to the 1/3. So we'll do the derivative of the outside, 1/3, times x squared plus 4, leave the inside alone, and then drop the exponent by 1. So 1/3 minus 1 is negative 2/3. times the derivative of what is inside. The derivative of x squared plus 4 is 2x. Low d high minus high d low. Now we put that over low low, which happens to be the denominator squared, x squared plus 4 raised to the, and you're going to square 1/3 power. That's power to a power, which means you have 2/3, right? Because you multiply when you raise a power to a power. So if you have a 1/3 power raised to the second, that's going to give you 2/3, in fact. Apparently I was explaining that in grand detail during class today. Let's now attempt to simplify this. Of course, we multiply by 1. It is itself, so you have an x squared plus 4 raised to the 1/3 power minus. I'm going to take that x times the 2x and times the 1/3, so that gives me 2/3 times x squared, and then that remaining factor is x squared plus 4, all raised to the negative 2/3 power. We still have in the denominator the same term, x squared plus 4 raised to the 2/3 power. Now at this point we want to try to simplify this fraction. Let's use the same technique that we did before for the numerator. Let's factor out the least power of any common factors. In this case, we both terms on top have an x squared plus 4. One is raised to the 1/3 power. The other one is raised to the negative 2/3 power. So that means the negative 2/3 power is the least of those two powers. Let's factor that out. And since it's in the numerator, I'm going to actually factor it all the way out front. So if I write out front x squared plus 4 times, raised to the negative 2/3. And, by the way, I want to go ahead and get rid of this 3 right here. That bothers me because that means I've got what we call a complex fraction, and we don't like complex fractions if we don't have to. So what I'm going to suggest that we do is let's go ahead and pull that 3 that's in a denominator of that second term out front. So basically I'm going to factor out 1/3 from both terms in the numerator. So if I write out 1/3 out here, then I have to think about what does that mean for this first term? What's left behind when I factor out a 1/3? Well, if it's a 1 there, then you divide out a 1/3 from it, you end up with 3 right here. Because what you want is that 1/3 times whatever that coefficient is on that first term needs to be 1. Okay, the second thing we're going to do is we're going to factor out the x squared plus 4 raised to negative 2/3. So you subtract 1/3 minus 2 minus a minus 2/3 is going to give you what? Think about that for a second. All right, that 1/3 minus a negative 2/3 should give me 1, which means what's really left behind is x squared plus 4 raised to the first power. Now, on the second term, we pulled out that 1/3. We're going to be left with a negative 2. That x squared is still there, and you factor that whole thing out so that all that's left there is a negative 2x squared. Denominators are the same. X squared plus 4 raised to the 2/3. All right. Now what I suggest that we do is let's rewrite this first one as a fraction. That is, that 3 is down in the denominator. That x to the negative 2/3 here is going to be moved down into the denominator. So it's really like an x squared plus 4 and with a 2/3 up there. All right. So with that done, the numerator, I got a 3x squared and a minus 2x squared is going to leave behind an x squared plus 12, right? 3 times 4 is 12. On bottom, I got the 3 from right here. I also have an x squared plus 4 Now I've got 2/3 power and a 2/3 power. Add those together, you get to the 4/3 power. And there is your final answer. So up here, after you took the derivative, you had a correct answer. But all the way down here is the fully simplified answer. I'll give you most credit for getting the quotient rule applied correctly, but however, you do need to make sure that you have it simplified. Okay. At this point during class, somebody asked, I believe, where I got the x squared plus 12. So I point out, remember, 3 times x squared is 3x squared plus 12 minus 2x squared. That's where you get that x squared plus 12. Always take a moment during class to offer a chance for anybody to ask any questions along the way. So I'm just double checking to make sure that anybody that might have questions can ask them. Again, I'm reminding you of the fact that in this particular portion of the lecture, my audio from class accidentally, or I don't know what caused it, but it went out. So until about time signature around 45 minutes or so, I'm going to be just doing a narration over what we've already done in class. So I'm doing this after the fact, narrating the best that I can. At this point, we want to talk about transcendental functions. We've talked about the derivatives that involve rational equations, kind of polynomial-like things, square roots. But what we have not yet talked about are things like sines and cosines. And again, we're doing this in the context of the chain rule, so we want to know when we have, say, functions of functions like sine of 2x. It works the same way. Your container function, your outside function, is the sine. One thing to be aware of, however, is that this is different than saying, parentheses sine of 2 times x. This means sine of the quantity 2x, which is sometimes left off. These parentheses here, the red ones, are left off in a textbook, but they're understood to be there, that you're taking the sine of that entire expression that follows. Now, if that is the case, then like I said, your container function is sine. That's the outside function. Derivative of sine is, cosine, right? You leave the inside alone, so derivative of sine is cosine, so it's cosine of 2x times the derivative of what is inside, which of course is 2. Derivative of 2x is 2. So that leaves you with 2 cosine of 2x. It's that simple. Not much to it. Okay. Let's do another one similar to that. We'll do one with a cosine in it this time. Y is cosine of, say, x minus 1. Took a second in class to let students try to work this one on their own. See what they come up with. Just remember, again, outside, take the derivative, leave the inside alone, and multiply by the chain. Don't forget to multiply by the chain, which is multiplying times the derivative of what's inside. So derivative of cosine is negative sine. Leave the x minus 1 inside. Derivative of x minus 1 is 1. Let's do one more transcendental function. We've done sines and cosines. What about exponentials? Now, don't forget, of course, that the derivative of an exponential e to the x, that's one of those beautiful things in mathematics. It's that special function that when you take the derivative of e to the x, you end up with e to the x, right? That's a basic fact that makes e to the x such a fantastic function. I think I even made a big deal about it in class at this point, reminding everyone of just how awesome and how much love I have for the e to the x function because of that property right there. I mean, I'm pausing right now in class just to go, isn't that great? Isn't that fantastic? All right, so y equals e to the 3x. The outside function is e to the u, right? So we will just say that the derivative of e to the 3x is e to the 3x. But now you got to multiply times the inside of that, which the inside is, of course, 3x. Derivative of 3x is 3. So instead of writing it after, I just put it in front. Alrighty then. Transcendental functions, we've got those taken care of. Now let's do one of these examples that I alluded to earlier where with the chain rule, called the chain because you can actually have several links in the chain instead of just one. What if you have a function inside of a function inside of a function? Which, here's an example where that is the case. If you have sine cubed of 4t. All right, again, you don't have the product rule in the sense that you're not talking about sine times 4t. You don't have any kind of quotient rule, sum difference. What you've got is an outside function. I asked the class what that was, and somebody recognized that it's the u cubed function, right? Because you can think of this as sine of 4t quantity cubed. Notice now you've got the outermost function is the cubing part. The next outer part inside of that is the sine, and then inside of that is the 4t. So you got a function inside a function inside of a function. All right, so if you do the outside one, you get 3 times, leave the inside alone, and then square it. Now the next outermost function was the sine, so you're going to multiply times the derivative of the sine of 4t. The derivative of the sine of 4t is going to be the derivative of the outside function times the derivative of what's inside. The outside function is sine, so derivative of sine is cosine. Right? So you write down cosine of, still leaving the inside alone, 4t. Now times the derivative of what's inside that sine function, which was 4t. What's the derivative of 4t? The derivative of 4t is 4. Okay? So, in the end, if you multiply the 3 times the 4, you get 12. You have a sine squared of 4t, and you have a cosine of 4t. And that is your final answer. There was a little confusion in class today about exactly where I got all those pieces, so I again went through and made sure that everybody was clear on where the different pieces come from, right? That sine squared notation, hopefully you'll remember from trig, is just another way of writing sine of 4t quantity squared. Right, the sign with the little exponent 2 is the same thing as sine of 4t with parentheses around it raised to the 2. Okay, so where did everything come from? This right here is the outer function taking its derivative, right? So 3 sine of 4t quantity squared. The next piece right here, the next whole piece comes from the derivative of sine of 4t with the 4t inside. You have cosine of then 4t times the derivative of the 4t part. Okay, so just here's some notation about where everything is coming from. Okay, so again, the chain rule is all a matter of derivative of the outside times the derivative of what's inside, and if you have to keep going, if there's more than one inside, you do inside, inside, so forth, all the way down until you've exhausted the chain. So the chain rule means multiply by the chain. Next, we have the ability to discuss a function that we've actually kind of skipped over. You know, if we're trying to get to the point that we can take the derivative of any function at all, then we've left one out, namely the natural logarithm. The reason why we've left it out until this point is while it's not a hard formula to know what the derivative of the natural log is, it is, in order to show where it comes from, we need the chain rule. So here's an explanation of how we come up with the derivative of the natural log of x. Start with just, let's say y is equal to natural log of x. We want to find the derivative of y with respect to x. So let's take, in this equation, of both sides. Meaning, let's exponentiate both sides. That is, write it as e to the y is equal to e to the natural log of x. Now, you remember what e to the natural log of x does? Cancels, and you're left with e to the y is equal to just x. So now take the derivative of both sides. Meaning, let's do d dx of e to the y and d dx of x. The right-hand side's easy. That's just 1. The derivative of x with respect to x is 1. Now here's where you got to be careful on the left-hand side. What variable are we taking the derivative with respect to? No, careful. There's a specific variable. Either x or y is the answer. Which variable are we taking the derivative with respect to? Look right here. If you take the derivative of both sides, it has to be with respect to the same variable in order for it to be equal. Okay? Now, we haven't really emphasized this yet, but we kind of assumed that whenever I'm taking the derivative, it's whatever variable I see there. But you got to be careful. There's a difference between the derivative with respect to y and the derivative with respect to x. Right? The derivative of this with respect to y is just e to the y. Right? But the derivative with respect to x, we have to consider that y up here is actually some function of x. Right? So this really is like a function of another function. And while we know what y is, and I don't want to plug it in yet, I'm going to just say y we know is some function of x. So I have to apply the chain rule right here. Because I'm taking the derivative of a function that is a function of another function. Right? This would be like e to the u, and u was some other thing. So the way that works is you take the derivative of the outside, which is still just e to the y, like you guys would have written down anyways, but times the derivative of what's inside. Now, we don't know what the derivative of y is yet. That's what we're trying to find. So let's just write it symbolically saying, well, whatever the derivative of y with respect to x is, that's where it goes. In fact, this right here is what we're looking for. We're trying to solve the equation for this. Now, here's the key. Look right here. What is e to the y the same thing as? It's x, right? So this means that actually what I have written here is x times dy dx is equal to 1. All right? So if I wanted to solve for dy dx, what can I do to this equation? Divide both sides by x. Boom, I have the derivative of y with respect to x is 1 over x. In other words, if y is the natural log of x, the derivative of y, 1 over x. So here's what we just proved. We just derived it ourselves from scratch. The derivative of the natural log of x is 1 over x. So there's a very important derivative formula that you need to know. Just like you know the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of e to the x is e to the x. Now the derivative of natural log of x is 1 over x. That is one you need to know. Okay? Dun, dun, dun. Example, what if I had the ddx of the natural log of 2x? This is the chain rule, right? So what's the derivative of the natural log of something? 1 over that something. In our case, the something is times the derivative of what's inside. Which is equal to what? One over x. Because the 2's. Okay. Maybe I want to emphasize something over here off the side. Notice, if you have the derivative with respect to x of something other than an x inside here, it's going to be 1 over u times u prime, because that's just the chain rule. Or sometimes we just shortcut it and go ahead and write it like this. Right, it's the derivative of what's inside over what's inside. Example, d dx, let's say, of natural log of x squared plus 1. And you can write it out the long way like I did before, where you first do 1 over what's inside times what's inside, its derivative. Or what I do is this. I know it's going to be 1 over the inside of the logarithm, so an x squared plus 1 down here. And then what's the derivative of the inside? 2x. Does that make sense to you? Now, oh, hey, where'd you go? There you go. Sorry. There is one technique that we spend a lot of time in our algebra classes making sure students know how to do. And we even talked about it briefly in this class, where we took a logarithm and expanded it. Do you remember using the properties of logarithms to expand a single logarithm into a bunch of different logarithms, either added together or subtracted together? Things like if I had natural log of x times y, I can write it as natural log of x plus natural log of y. Does that ring a bell? Natural log of x over y is minus, and then natural log of, say, x to the nth. Anyone? Anyone? Bueller? Bueller? No? Oh, come on. You've done it. You actually did it in your homework. Oh, assuming you did your homework, I guess. Or didn't skip that problem. What can you do with that n? You move it out front. You can write that as n natural log. Oh, that's not a natural log. That's an h. Natural log of x. Right? So if it had been natural log of x cubed, you could write it as 3 natural log of x. Okay, now, here's the thing. I don't know if you pay attention, especially those of you that took college algebra here. When we covered this in college algebra, we made a big deal about how you can go one direction and you can expand these logarithms out. And then we made a big deal about how you can combine them into one logarithm. So these equations work in both directions. And yet, in that class and in our algebra, the only thing we ever really needed in algebra was to go this way. Meaning, from right to left, we want to be able to combine them so that whenever we solved logarithmic equations, we can get them all into one log. We never told you why you wanted to go the other way. Would you ever want to go the other way? Okay? There was actually no application whatsoever where that was useful in algebra. I like when we sneak things in like that, where there's no reason to ever do it in that class, but there's some lurking reason way far down the road. Guess what? We reached that point. The reason why we tell us to go the other way is that it makes life in calculus easier. There's a few things hidden throughout algebra and trigonometry that the only reason we teach them is to make life easier once you get to calculus. Okay? Let me give you an example of what I mean. If I gave you the natural log of x times x squared plus 1 squared divided by the square root of 2x cubed minus 1. Without the properties off to the right there, that's just mean for me to assign to you. Because what would you have to do? You would have to take 1 over this, which is just clipping it, and then take the derivative of this, which is now low-d high minus high-d low over low-low, which has all kinds of crap in it, right? Not that you can't do it. It's actually pretty easy. In fact, all derivatives are fairly easy once you get down those 5 rules, the sum, difference, product, quotient, and chain rule. But that's just long, right? Expand first. Now, what do I mean by expand? Well, I can apply all 3 of these rules right here to rewrite this expression. First of all, it's a quotient, right? So it's like the numerator, natural log of the numerator, x squared plus 1 squared, minus the natural log of the denominator, which is square root of 2x cubed minus 1. By the way, as always with derivatives, what do I actually want to do with that square root? Turn it to a fraction, so write it to the 1/2 power. See how I did that? Something over something inside the log is the subtraction of those 2 logs. What about this product right here? Well, I can also use the first rule and write that as the natural log of x plus the natural log of x squared plus 1 squared minus the natural log of 2x cubed minus 1 to the 1/2. You with me? No? Yes? Okay. And then what can I do with this 2 right here and this 1/2 here? Move them out front. Natural log of x plus 2, natural log of x squared plus 1 minus 1/2 the natural log of 2x cubed minus 1. Okay? So now the derivative, right, let's just call this y so I can write this as y prime, would be the derivative of each of these separately, which is now pretty much a piece of cake. Right? What's the derivative of the natural log of x?
1 over x.
Plus, now the 2 is going to just hang out. What's the derivative of natural log of x squared plus 1?
2.
You put the x squared plus 1 in the denominator, right? And then in top you multiply times the derivative, so a 2x up there. Right? 1 over what's inside times the derivative of what's inside. And then minus, you got a 2 down here on bottom now from this fraction. You put the 2x cubed minus 1 down here, and you've got 6x squared on top. In other words, you have 1 over x plus 4x over x squared plus 1 minus this 2 cancels with 2, leaving a 3, 3x squared over 2x cubed minus 1 is the derivative. And that is a whole lot easier, a whole lot less work than it would have been to try to take the derivative of what's inside there and then simplify it after you're done. Is that good news? That's good news.
Yes.
Okay, last thing. Any questions about that one before I move on? Okay, so thinking through all the functions that we can take the derivative of right now. We've got all polynomials. We've got all rational functions. Any square roots with stuff inside of them. Any roots at all with stuff inside of them. All the trig functions. Sine all the way through cotangent. We've got e to the x. We got the natural log of x. Is that everything? Is that all we ever cover? Can you think of any other functions we're missing? Arc? You were going to say arc?
Do we take the arctangent?
Arctangent. Okay. Very good point, and we will cover those in a whole section dedicated to inverse functions. So that's one set we still need to address. Okay? I got another one in mind, though. You get to play the favorite game of guess what the professor's thinking. Yay! Well, let me give you a hint. E to the x and natural log of x. Exponentials, logarithms, right? So we've talked about the base e. What about something else to the x? Right? Say 2 to the x, 3 to the x, 5 to the x. Do we know how to take the derivative of those? Other bases, right? What is the derivative, consider, of, say, 2 to the x? And it is not x2 to the x minus 1. Right? If you were tempted to do that, let me just cut you off right now and say, no, it doesn't work that way. It's when you have a variable down here and the number up here that the power rule works. Okay? But this right here is wrong. Okay? So how do we do that? Well, I'm going to go ahead and work this out for you real quick. I'm almost out of time, but the technique is the same thing that I used back before, was to think of y as 2 to the x. And instead of taking the exponential of both sides, let's take the natural log of both sides. Which means the natural log of y is equal to the natural log of 2 to the x. Okay, now on the right hand side, what do you see that we could do? Just like that. So you have the natural log of y is equal to x natural log of 2. Okay, so far so good. Now I'm going to go back and I'm going to do the e to the x of both sides, the exponentiate both sides. Kind of undo what I just did. All right, so e to the natural log of y equals e to the x natural log of 2. The reason I do that is on the left I still just have y now, because e to the natural log of y is y. E to the x natural log of 2. So apparently 2 to the x, according to this technique right here, is the same thing as e to the x natural log of 2. Those are equivalent functions. And now having written it this way, we can use the chain rule. Y prime would be the derivative of the outside function, which e to the x natural log of 2, times the derivative of what's inside. Now what's the derivative of just x natural log of 2? Don't make it too complicated. The natural log of 2 is a number, right? It's some decimal number, 0.9 something, right? So if you ignore the natural log of 2, the derivative of x is just 1, but the constant, the number, hangs out, right? So that's natural log of 2. Right? That'd be like, what's the derivative of 2x? The derivative of 2x is 2. What's the derivative of 3x? It's 3. The derivative of x natural log of 2 is natural log of 2, because it's just a number times x. right? I mean, I could have even just written it as natural log of 2, the number, times x. The number hangs out. Okay, so the derivative of that would be natural log of 2. And of course, again, recognize that right there is the same thing as 2 to the x. So the derivative of 2 to the x is 2 to the x times the natural log of 2. Or in general, the derivative of a to the x is always a to the x times the natural log of a. Okay, so that's one other formula to remember. Let me write down one last one, and then I can say goodbye to you. The derivative of the natural log base a of x, which is the other function I was thinking of that we haven't done yet, is actually 1 over the natural log of a times, no, 1 over x natural log of a. I wrote down the wrong thing. There we go.
Isn't it times the...
Yeah, the natural log of a is what comes in right here. Where this comes from, by the way, is that the log base a of x is always the natural log of x over the natural log of a. And so if you take the derivative of that, you end up with 1 over x times the natural log of a. Okay? All right, so that is all of section 2.4. You do have a homework assignment. Make sure I get your homework before you leave today. Okie dokie? And I'll try to get this posted on Blackboard, this video, sometime this afternoon.